Okay. Hi. So today we will discuss X-ray diffraction. The X-ray are a part of electromagnetic spectrum which has wavelength ranging from zero point 0.1 angstrom to 100 angstrom. Since their wavelength is of few angstrom order, they can be used to study the crystal structure of different materials, different solids, for example. Because for the diffraction, we need a condition that the electromagnetic waves that we are using, their wavelength should be of the order of the dimension of the object with which they are interacting. So in that sense, X-rays seems to be a very effective tool in exploring the properties of the different crystals, because interplanetary spacing is of the order of few angstrom, 1 angstrom, 2 angstrom of the order. So for that, in that sense, XRD is one of the major tool to study the structural properties of the crystal. So for example, the famous equation that is used to study the XRD patterns of these solids is known as Bragg's law, Bragg's condition. Or Bragg's condition, which is, suppose this is the arrangement of atoms in a crystal. What is a crystal? Crystal is a periodic arrangement of atoms, ions or molecules. So suppose this is these are the arrangements of atoms in a particular solid, and X-ray is coming from this direction, suppose, and it get diffracted, and the other X-ray is coming in this direction, get diffracted along this. Suppose this is one coming in and one getting diffracted, the two ray coming in and the second ray getting refracted. So these two rays actually has a phase relation between them, because there is a path difference. Suppose this is one plane and this is another crystal plane. The distance between these two planes, which are parallel planes, is, let's say, DHKL, where HKL are the Miller indices of these planes, and the parallel planes have the same Miller indices. So okay, so what is the path difference between these two rays? Rays number 1 prime, or this one O1 prime, and let's say, let me call it as O1, this we call it O2. So what is the path difference? The path difference between 1 prime, 1 O1 1 prime and 2 O2 2 prime rays. The path difference is equal to this much. Suppose this I give a L and M name, and this path difference is this much, LO2 plus O2 M. Suppose now let's say this angle is theta. Okay, this is called Bragg angle. So if this angle is theta, by the geometry you can see that this angle is actually equal to theta. Okay, so if this is the case, so this O to L distance, this comes out to be d sine theta, because this is DHKL. So this is also DHKL. So if we apply sine theta, that is this upon this. So the sine theta from this figure is actually equal to LO2 divided by over O2, and LO2 is nothing but DHKL, and this O1O2, LO2 is, we have to find out, and O1O2 is DHKL. So that is, this LO2 is DHKL sine theta. Similarly, if we see this triangle O1, O2, and this is O1, O2, and M, we get the same thing. So this is basically equal to 2DHKL sine theta. So this path difference, if this path difference is equal to, if this is equal to n lambda, if path difference 2DHKL KL sin theta equal to n lambda. Okay, n is the order of diffraction, that gives us constructive interference. Interference between these two. This is known as Bragg's law for X-ray diffraction. This is the master equation. We can draw a lot of information about the crystal using this simple technique called XRD. Now there is something called structure factor, or which we have to define to study further, that how we can actually determine whether our solid is, or the crystal is BCC or FCC or simple cubic or any other crystal structure. So before we do that, so we will have to define a term, atomic form factor, which is basically the ratio of the amplitude diffracted by an atom as a whole and the amplitude of the X-ray diffracted by a single electron. Similarly, we define another term which is called capital F, and this is in general complex in nature, so we put a modulus sign here. So this is called as scattering factor, structural factor, sorry, not a scattering factor, structural factor, which is defined as the amplitude of X-ray diffracted by a unit cell and divided by amplitude of X-ray diffracted by an electron. What is a unit cell? Unit cell in a crystal is that region which on repeating in every direction will generate the entire spaces without leaving any void or overlap. Okay, so that is called unit cell. So unit cell in general may have one atom, more than one atom, right? It depends on the crystal structure. For example, for simple cubic, it has effectively only one atom in the unit cell, and for BCC there are two, and for FCC there are four. Okay, we'll see that. So when we find out this ratio and do the mathematics of it, we get this relation that this F is actually equal to FHKL for the crystal plane with having Miller indices HKL. This is equal to, this comes out to be Fn e to the power 2 pi iota HUN KVN plus LN, where n runs from 1 to capital N. Okay, where UN, VN and WN are the coordinates of the atoms, and this HKL are the Miller indices of the plane. Right? So intensity of the diffracted X-rays actually proportional to this modulus F square. So intensity is proportional to modulus of F square. So we will see for different crystal structure now, for example simple cubic, BCC or FCC, in what condition on HKL we get a non-zero intensity. Because if we get a non-zero intensity of a diffracted X-ray, it means we are going to get some diffraction for those particular HKL set of values, for which this is non-zero. If it is zero, it means we don't get any diffracted beam. This means that Bragg condition is not being satisfied for those set of HKL. Okay, so let's try to see. So I will write down the F again here, which is summation F HKL e to the power 2 pi iota H. This, let me put a HFN here, sorry, that's the HUN and KVN and LWN. All right. Fine. So where n runs from number 1, n runs from 1 to capital N, where capital N are the number of atoms in a unit cell. Okay. So for example, let me take the example of a simple cubic. So simple cubic, Simple cubic is a case when we have a cube, for example, and 8 atoms are there at the 8 corners of a cube. So effective contribution of one single atom to this cube is 1/8, because if this one single atom at the corner of a cube is being shared by the 8 different cubes, if we extend this structure in all 3 dimensions, so this is being shared by the 8 cubes. So the effective contribution of the one single atom to this particular unit cell is 1/8. So there are 8 in number, so 8 into 1/8 is 1. So effective number of atoms in a number of atoms in a unit cell, in a number of atoms in a unit cell of a simple cubic is actually equal to 1. That means if we want to actually calculate this capital F, this will have only one single term, where we have only n equal to 1 to 1, right? This has only single. And what is the position of this one single atom? This can be assigned to 0, 0, 0. That is the origin. So for that, if we calculate F, for example, that comes out to be F, suppose this is F for 1, and there is 1, so we can write down F. There is a one single term in the summation only, so I can put F without any subscript to it. So 2 pi I, and then this is 0, 0, 0, so this is basically 0. And because U and Vn and Wn, these are 0, 0, 0, because of this position of that atom, that is correspond to one single unit cell of this simple cubic, the position of that atom is 0. Position of that atom is 0. So 0, 0, 0. So that comes out to be actually F, that is non-zero. So intensity in that sense is proportional to modulus F square, which is modulus F square, so which is non-zero. So it means what? There is no condition on HKL, since the position of the effective atom that is associated to one single unit cell of simple cubic, that is 0, 0, 0, 0, 0. So for any values of HKL, this condition will always satisfy that the intensity for any value of HKL is going to be non-zero. It means all kind of reflections are allowed in simple cubic. Okay, for example, HK, it could be 1, 0, 0, 0, 1, 0, or 1, 1, 0, or 1, 1, 1, or etc., 2, 2, 2, etc. Any kind of reflections are allowed, because there is no condition on HKL. Now let's discuss the case of BCC, for example. Now in case of BCC, that is body-centered cubic, we have this kind of unit cell, the same cubic one as we had the earlier, 8 atoms at the corner and what at the center of the body. So one contribution, effectively one contribution due to the 8 corners and one right at the center of the body. So there are effective number of atoms in the unit cell of a BCC, number of atoms in unit cell of BCC is equal to 2. Okay, and then if we apply and what are the position of these atoms? This position of these atoms could be taken as 0, 0, 0, 0, 0, and let's say half, half, and half. Okay, so that will give me F as it will, now it will have 2 terms. Now since we are considering all the atoms are of the same kind, so F is not going to change for one atom to different atoms, or it will be same for all the atoms in unit cell, because we are considering this, these all atoms are of same kind. If they had they been of different kinds, then this F would have been different for all the atoms. Okay, so now since they are of same type, so let me take that F only and e to the power 2 pi iota, and this first one will give me 0 and the second one give me e to the power 2 pi iota by 2 h plus k plus l. Okay, which means I will have F plus f e to the power pi iota h plus k plus l. Now if we look carefully that if this h k plus h plus k plus l is an even number, if this is an even number, so this will give me e to the power even number times pi iota, which means this factor will give me unity for h plus k plus l to be even. So that in that case f plus f will be 2f, will give a non-zero magnitude of capital F, that is non-zero intensity. But if this is an odd number, h plus k plus l is an odd number, so we will have an odd number times pi iota, which will give me this factor as -1. So f minus f would be 0. So the capital F would be non-zero for h plus k plus l to be even, and it will be 0 for h plus k plus l to be odd. So what I mean to say is that from here we can conclude that if h plus k plus l is even, we get capital F as 2f. So intensity will be proportional to modulus f square will be proportional to 4f square. Okay, non-zero. And if h plus k plus l is odd, we are going to have intensity f to be 0. That means intensity to be 0. Okay, I mean no diffracted beam in this case. It means Bragg condition is not getting satisfied for those planes for which h plus k plus l is odd. So in case of BCC, the allowed reflections have become, in case of BCC, the body-centered cubic, allowed reflections are for example, for which h plus k plus l is even. For example, it's a 2 0 0, 0 2 0, etc. etc. Before that, even 1 1 0, because you see that h plus k plus l is even for 1 1 0. Okay, or 1 0 1 or 0 1 1. 1 0 0 is not allowed because 1 0 0 will not give you the planes which have Miller indices 1 0 0. In BCC they will not give you Bragg reflection, because for 1 0 0 it will be 1 0 0, that will become odd, and odd will not give. So 1 0 0, 0 1 0 or 0 0 1 will not give. So 1 1 0 or 0 0 1 or 0 1 1 or 1 1 0, this type of plane will give for which h plus k plus l is even. Similarly 2 0 0, 0 2 0 or 0 2 2, for example. All these things, all these planes will give the Bragg reflection in case of BCC. Okay, so similarly for FCC, in case of FCC, we have this unit cell. So we have at the 8 corners all the atoms, and then center of each phase, one at the front and one at the back one. So these are 6 faces, 1 2 3 4 5 6 and 8 corners. So due to the 8 corners, the effective contribution is 1, and one face centered atom is shared by 2 faces, so it has half contribution to the one unit cell. So 6 into half of atoms in a unit cell of FCC structure is 6 into half. This is due to the face centered atoms. This contribution is due to the face centered atom, and 1 due to the corner atoms, which can be written as 8 into 1 over 8. We are just discussing case of simple cubic. So this gives me effectively 4. So 4 number of atoms, and the positions that can be taken as of these 4 atoms: 0 0 0, 0 half half, half 0 half, and half half 0. Okay, so these are the positions. So if we want to find out the capital F, for example, in case of FCC, so what we get as F, we have 4 terms this time. So this first one will be F because of this 0, f into e to the power 0 plus f into e to the power 2 pi iota times, if I take this, so this will give me half of k plus l, and this will give me f into e to the power 2 pi iota 2 pi iota h plus l plus f into e to the power 2 pi iota by 2, of course, and there's by 2 and again by 2 h plus k. Okay, so that's what we get, and we get f plus f into e to the power pi iota k plus l plus f into the power pi iota h plus l plus f into the power pi iota h plus k. What we see in case of FCC, that's what we get. So if HKL are mixed indices means if HKL are of mixed nature, of even and odd, means if out of these three, let's say one is odd, rest of two are even, of two are even, one is odd, then we'll see that these three terms, out of these three terms, one will be positive and rest two will be negative whenever this condition is satisfied. For example, if I take an example of, let's say, 101, where 1 is odd and 0 is even. So in that case, k plus l is 0 plus 1, that is odd. This will give him f minus f here. This will cancel out this, and in that case h plus l, 1 plus 1 will be even. This will give me plus f, and h plus k will give me again odd, so this is minus f. So this will cancel out this. So exactly this capital F would be 0 in that case. It means the intensity would be 0, no Bragg refraction. For those values of HKL, no Bragg refraction. For those values of HKL for which we are getting the mixed indices of this HKL, mixed nature of this HKL, we have not get any diffracted beam. But if HKL are all odd or all even, in both the condition, if they are all odd or both are or all are even, in that case the sum of two odd number is even and sum of two even number is again even. If they all are odd, there are some coming in pairs of these Miller indices. Okay, so this will be even again because odd plus odd will be even, odd plus odd will be even, odd plus odd. So ultimately we'll have capital F to be 4F. In case HKL all are odd. All are odd. If they are all are even, then even plus even is again even plus even is again even plus even is again we have the same thing. Okay? So we get the same thing 4F. HKL all are odd or even. So in that case, intensity is proportional to modulus F square, that is proportional to 16 F square, non-zero. So we'll get Bragg reflection. So all those values of HKL for which these conditions are satisfied will get Bragg reflection in case of FCC. So for example, they could be like 100 will be there or not in case of FCC. No, because 1 is odd, 00 is even. So there is a mixing. So 100 will not give any peak in case of FCC crystal. Or the 110, for example, 110 again 2 are odd, 1 is even, not possible. 111, yes, it is possible because all are odd. Similarly, 200 is possible because all are even. 210 is not possible because 2 is even, 0 is even, 1 is odd. Okay, so this is how we actually can predict out by what kind of peaks would be present in what kind of crystal structure. I've taken the example of simple FCC, BCC and simple cubic, but this argument can be extended to HCP and NaCl structure or other KCl structure or other structure as well. Okay, So now the question is, suppose I ask a very simple question, that how do you predict whether you have been given an XRD data of a sample and you have been asked to find out whether the crystal structure is present in your sample. Is it simple cubic, FCC or BCC? Suppose there are three choices only. It could be either simple cubic or BCC or FCC. In general, it could be of different other crystal structures also. But let's say, suppose for the time being, there are only three possibilities for a particular sample to be simple cubic, FCC or BCC. So what kind of crystal structure is present? DHKL is equal to, for the cubic system, under root h square plus k square plus l square, where a is the lattice parameter, and for a given cubic is lattice parameter, that is the edge of the unit cell. For a given cubic crystal structure, this is a constant, so I can write down a is a constant for a given cubic system. I can write down this DHKL is proportional to this. In other words, 1 over DHKL square is proportional to h square plus k square plus l square. And we also know that the Bragg's diffraction condition is 2DHKL sine theta equal to lambda, and lambda n is 1 for principal maxima that we observe in experiment. This equation tells us that the sine square theta is actually equal to lambda square upon 4 DHKL square, which is proportional to, for a given X-ray wavelength lambda, which is quite often for most of the samples used as copper K alpha radiation, 1.54 angstrom, which that is also fixed, that is proportional to 1 over DHKL square. And we have just seen that for a cubic system, 1 over DHKL square is proportional to h square plus k square plus l square. Okay, now we have to see that what are the possible values of this sine square theta for a simple cubic, for example. So in case of simple cubic, what are the allowed values of HKL? Allowed values of HKL in case of simple cubic is, allowed values of HKL are, there is no condition on HKL. So 100 or 110, 111, 200, 220, 222, all, or rather in between 210, all these values are allowed. Okay, so like if I write down in a proper sequence that it is 200, then 210, 211, and then 220, okay, and then so forth, and so on and so forth, 222, and so if we calculate, for example, this h square plus k square plus l square, allowed value of this h square plus k square in case of simple cubic, that would be 100 is 1 plus 0 plus 0 1 plus 1 plus 0 is 2, and then 3, and then 4, and then this is 3, h square plus k square plus l square, for this is 3, for this it is 4, for this it is 5, for this it is 6, this is 5, and for this it is 6, and for, let's say, simple cubic, if this ratio is in case of simple cubic, the ratio of h square plus k square plus l square, it comes out to be in this ratio, 1 plus 2 plus 3 plus 4 and 5 and 6 and so on and so forth. Similarly, if we check out, this is the value of h square plus k square plus l square, ratio of h square plus k square, the ratio of h square plus k square plus l square. In case of simple cubic, it is this. In case of let's say FCC, in case of FCC, HKL mixing is not allowed. HKL are either odd or HKL are either even. So FCC is 100 is not allowed because it's a mixing case. So 110 is similarly again not allowed. 111 is allowed in case of FCC because all are odd. Then 211, 201 again not allowed because it's a mixing case. So what is 200 is allowed. Okay, and then 220 is allowed, 222 is allowed, and before 222 there would be a term called 131 that is also allowed, because 1 plus 9 plus 11 and this is 2. Fine. So if you see in case of FCC, the allowed value is of h square plus k, because this is all odd, it is allowed in FCC, it is all even, again allowed in FCC, and this is again even, this is odd, this is even, and so on and so forth. So this FCC would be 3 is to 4 is to 8 is to 11 is to 12 and so on and so forth. Similarly, case of BCC, if we see these values, what are the allowed values of HKL? In case of BCC, if HK plus L is even, then we get the value, then we get the intensity, refracted intensity. Otherwise, for odd, we don't get a value. That's what we had seen in case of BCC. So HK plus L, HK plus H plus K plus L to be even. So it means the 100 is allowed. No, because the sum is 100, the sum is odd, so it's not allowed. So 110 is allowed because the sum is even. Right? So similarly, next possible choice would be, let's say if I take 111, the 111 will be odd, not allowed. 200 is allowed because sum is even. 210 is not allowed, sum is odd. 220 is allowed, sum is even. Okay, and similarly 112, this is also allowed because sum is even. Now we have to see which peak will come first, 220 or 112. So for that we have to see this, for which h square plus k square plus l square is higher, theta will be higher. So for this h square plus k square plus l square is 4 plus 4 8. For this it is 1 plus 1 plus 4 6. So this will come first. So this will 112 will come first and 220 will come 0. Because for this is higher, it is 8, and for this it is 6. So this will come first. And so if we see that the ratio is, let's say 2 is to 4 is to 6 is to 8 and so on and so forth. So what we have to do is we have to find out from the, so to answer the question that I asked in the beginning is that if I have been given a sample, XRD pattern of a sample, and you have been asked to find out which crystal structure out of these three possibilities, simple cubic, FCC or BCC is present. So we have to, what I will have to do is I will have to find out the ratio of sine square theta 1, for example, this is theta 1, theta 2, theta 3, the given XRD pattern. I can find out sine square theta 1, sine square theta 2, sine square theta 3, and so on and so forth. If that ratio matches with this, then the structure is a simple cubic. If the ratio matches with this, the structure is FCC. If the ratio matches this, the structure is FCC. The structure is BCC. So this is how we can, on the elementary level, predict out of these three possibilities. There are other possibilities also, like HCP and NaCl structure, KCl structure, and other things that can, this logic can be extended out to them also.